Okay, so we will continue. We derive the torque expression. So do you remember from the previous class? So we know the mechanical power. This is from the previous class. So I will have here the mechanical power is equal to, this is the stator active power plus the rotor active power. Okay, minus, this is the stator losses minus the rotor losses. Okay, so we have already demonstrated the stator active power. Okay, the stator active power is equal to 3 times, this is the stator resistance, okay, times the stator current square. Okay, this is phasor. Plus 3 times, I will take the real part. Okay, I will have here the speed. This is the angular frequency. I will have here the magnetizing inductance. Okay, this is the rotor current. So this is phasor times the conjugate of the stator current. Okay, so we demonstrated in the previous class this equation. In a similar way for the rotor, this is the rotor active power. I will have 3 times the rotor resistance times the rotor current square plus is similar, so I will have 3 times the real part J, this is the angular speed, okay, this is the magnetizing inductance. I will have the stator current, this is phasor, times the conjugate of the current. Okay, so what about the losses? How to compute the losses? For the stator, we know the rotor active power losses is equal to 3 times, okay, the rotor resistance times the rotor current square. Okay, for the stator, I will have 3 cables too, so therefore this is equal to 3 times. I will have the stator resistance times the stator current square. Okay, so what I want is to derive the torque expression. Okay, so let's substitute this into this equation. Let's substituting in this equation, substituting in this equation, and substituting in this equation. So what happened? I will cancel off. I will cancel off. Yeah, I will have these two terms, right? I will have these two terms. Okay, so finally the mechanical power is equal to 3 times, taking the real part. Okay, so I will have J, this is the angular speed, this is the speed, this is the magnetizing inductance, okay, times the rotor current, this is phasor, times the stator current, this is the conjugate of the stator current, okay, this is my first term. What about my second term? I will have 3 times the real part. Okay, I will have J, this is the slip, times the speed, times the magnetizing inductance, times the stator current. This is phasor times the rotor current. This is the conjugate. Okay, this is the conjugate. Okay, so taking out the common factor, I'm taking out this common factor. For instance, this speed, this is the common factor. The magnetizing inductance is the common factor, and the slip. Yeah, so I will take this common factor, right? So I will say the mechanical speed. Taking out this common factor, I will have, even I will take out the negative, okay, in order to apply an identity, okay, so I will have 3 times. So this is the common factor. This is the angular speed, angular frequency, sorry. So I will have here the magnetizing inductance. Okay, what else? Taking out the speed, so I will have 1 minus s. Okay. And then I will have here the real part of this term and the real part of this term. Okay, it means this is an identity. Okay, so I will have the real part. Okay, so I will have here J, the rotor current, times this is the conjugate of the current. Okay, plus this is my first term, right? This is my first term. So taking out these factors, I will have this and this. Okay. On the other hand, I will have here the same. I will take this and this, the real part. So I will take the real part. Okay. So I will have the rotor current, phasor, phasor, phasor. Okay, times the conjugate of the stator current. This is an identity, okay? This is equal to the imaginary part, okay? The imaginary part of the rotor current times the conjugate of the stator current, okay? Therefore, I will have here times the imaginary part, I will have here the rotor current using this identity, right? Using this identity, okay? So I will have here times the stator current. So this is the mechanical power. Okay, but I want to derive the torque equation, okay? I want to derive the torque equation. Therefore, by definition, we know the mechanical power, okay, is equal to the electromagnetic torque times the speed, okay, times the speed. Okay, and this is equal to, substituting the speed, I will have here the electromagnetic torque times the mechanical speed over the number of poles. So I will have, this is the mechanical power, so therefore I have isolating the electromagnetic torque. Isolating the electromagnetic torque, I will have, so this is the mechanical power, okay? Substituting in this equation, isolating the electromagnetic torque, okay, so I will have the following equation. So the electromagnetic torque, okay, is equal to 3 times. I will have here the number of poles, the magnetizing inductance, okay, and times the imaginary part of the rotor current. This is the conjugate times the stator current. Okay, this is my final equation. But instead of the current, we use the fluxes in the torque expression. So we can achieve several equivalent torque equations, okay? So for instance, I will say this is my equation. Okay, so I will replace the stator current, okay, is equal to the stator flux over the stator inductor. Okay, so I will replace this equation here. Okay, I want to derive my new equation. Okay, therefore the electromagnetic torque. Okay, so taking out this factor, okay, taking out of the imaginary part because is real, this part. Okay, so I will have 3 times the number of poles, okay, times the magnetizing inductance. Okay, so substituting this equation into here and taking out this factor out. So I will have here the stator inductance times the imaginary part. So I will have here the flux, the stator flux times the conjugate of the rotor current. Okay, this is an alternative expression. So we can achieve several equivalent torque equations, okay? On the other hand, I want to use the rotor current. So once again, by definition, is equal to the rotor flux, okay, over the rotor inductance. So once again, substituting this equation here, okay, I will get the electromagnetic torque is equal to 3 times. So taking out the rotor inductance, okay, times the number of poles here, okay, and the imaginary part. So substituting here I will have here the rotor flux. This is the conjugate times the stator core. Okay, so I have many expression for the torque. Okay, even if I want to use the leakage coefficient, so do you remember the leakage coefficient is equal to 1 minus the magnetizing inductance square over, I will have here the stator inductance over the rotor inductance. This is the leakage coefficient, okay? So including or substituting in this equation is possible to get my final equation. So the electromagnetic torque, okay, is equal to 3 times the magnetizing inductance, okay? This is over the leakage coefficient times the rotor inductance times the stator inductance times the number of poles, okay, times the imaginary part of the rotor flux. This is the conjugate of the rotor flux, this is phasor 2, times the stator flux, phasor. Okay, so I have many expressions, okay? I have many expressions. If instead of the current we use fluxes, so I will have many expressions, okay? So in this way, we will compute the electromagnetic torque, okay? So what is missing is to compute the reactive power expression, okay? So let's continue with the reactive power expression. So do you remember from the previous class, I will use a similar way to active power expression. So how to compute, for instance, the reactive power and the active power? So from the previous class, we compute the stator active power, and this is equal to 3 times the real part. Okay, I will have here the stator voltage. This is phasor times the stator core. This is phasor 2. From the previous class, we demonstrate the stator voltage is equal to, I will have the stator resistance plus J, this is the speed, times the leakage reactance, times, I will have here the stator current, plus J, I will have here the speed, times the magnetizing inductance, I will have here the stator current plus the rotor current. Okay, this is from the previous class. We demonstrate these two equations. Okay, but now I want to compute the stator reactive power. Okay, so instead of the real part, I will take the imaginary part. Okay, so in order to compute the stator reactive power, this is equal to 3 times. Now taking the imaginary part, okay, of the stator voltage times the stator current. Because that is the way in order to compute the stator reactive power. Okay, the stator reactive power. So let's call this equation number 1. Okay, and let's call this equation number 2. So substituting equation number 1 into equation number 2, okay, I will get the reactive power. This is the stator reactive power. Okay, is equal to 3 times. I will have here the imaginary part. Okay, so I will replace the stator voltage. It means substituting this equation, and each term is multiplying by the conjugate of the stator current. Okay, so I will have the stator resistance times the stator current. It means this term plus this term plus this term. Okay, so I will get the conjugate of the current. Okay, plus I will have here my second term. I will have J times the speed, the stator speed, times the leakage reactance times the stator current times the conjugate of the stator current. So this term plus this term is the stator current square, right? Okay. This term plus this term is the stator current square. And what about this last term? So I will have plus J. I will have here the speed. This is the magnetizing inductance, okay, times I will have the stator current phasor. This is a phasor plus the rotor current phasor times the conjugate of the stator current. Okay, the conjugate of the stator current. Okay, this term is neglected because include the resistance. What I want is to compute the reactive power. Okay, that is the reason this term is neglected. Okay, the stator current times the conjugate is equal to the stator current squared. Okay, so therefore, the stator reactive power, okay, the stator reactive power is equal to, so I will have 3 times the imaginary part. Okay, so I will take the common factor. This time this is the stator current square. Okay, so I will have the stator current square. In this case, this time this is equal to the stator current square. So taking out the common factor, I will have 3 times the speed times the stator inductance times, okay, so I will have here the, this is the speed, sorry. This is the speed, so I will clear this. So this is a constant, okay, therefore it's possible to take out this term, okay? So I will have 3 times, this is the speed, okay? Yeah, I will have plus 3 times, this is the imaginary part, okay? So I will have J, the speed, this is the magnetizing inductance, okay? This is the rotor current times the stator current, this is the conjugate. This is my equation, this is the final equation. Okay, this is the final equation. Okay, so once again, I will apply a identity, okay? Identity, okay, so this is the imaginary part. So I will take J, okay? I will have only these two currents. Okay, so therefore, the identity is the imaginary part of J, the rotor current phasor, okay, times the conjugate of the stator current. This is the imaginary part, is equal to the real part, okay? I will have here the rotor current times, I will have here the stator current, but in this case, applying the conjugate, right? This is the identity. Okay, so therefore, using this identity here, using this identity in this equation, I will get the final equation. Okay, so I will get the final equation. The stator reactive power, okay, is equal to 3 times the speed times the stator inductance times the stator current square plus, I will have here 3 times the speed, okay, the magnetizing inductance, and using the identity, so I will have the real part, okay, of the rotor current, this is phasor, times the stator current, this is the conjugate, phasor 2, okay. This is the formula in order to compute the stator reactive power. In a similar way, I am able to derive the rotor reactive power. Okay, so In order to compute, so from the previous class we know the rotor active power is equal to 3 times. Taking the real part, okay, so I will have here the rotor voltage times the rotor current, okay? So by definition, the complex power is equal to the active power plus the reactive power. If I take the real part, this is the active power, okay? The imaginary part is the reactive power. Okay, and from the previous class, we derived the equation of the rotor voltage. The rotor voltage is equal to, I will have the rotor resistance plus J, okay? I will have here the slip. This is the angular frequency, the speed. I will have the leakage reactance times the rotor current. This is phasor, okay? Plus J, I will have the slip. This is the angular frequency times the magnetizing inductance times the stator current plus the rotor current, okay? So in a similar way, I will compute the reactive power. Instead of taking the real part, I will take the imaginary part. So taking the imaginary part, in order to compute the rotor reactive power, this is equal to the imaginary part of the rotor voltage times the rotor current. This is the conjugate, okay? So following the same methodology for the stator reactive power, the equation, the rotor reactive power is equal to 3 times. I will have here time the slip. This is the angular frequency. The rotor inductance. I will have here the rotor current square. Okay, so plus 3 times. Okay. The slip, I will have here the angular frequency times the magnetizing inductance, using once again the identity. So I will have the real part of the stator current times the rotor current. So we have already derived the equations for the active power, for the reactive power, for the electromagnetic torque, okay, and for the electromagnetic torque. Okay, so I will continue computing an approximation. I will call this the approximate relation between active power, torque, and speed. Some approximations. Okay, so I will use the previous equation. So we have already demonstrated the stator power. For instance, the stator active power is equal to 3 times the stator resistance times the stator current squared, plus I will have 3 times the real part. So we have already demonstrated for the active power and for the reactive power, right? So I will have J, this is the angular speed, the magnetizing inductance. This is the rotor current, this is phasor, okay? This is the stator current. So we have already derived this equation in the previous class. This is for the stator active power. For the rotor active power is equal to 3 times. I will have here the rotor resistance times the rotor current square plus 3 times the real part, okay? So I will have here J. I will include the slip for the rotor. So I will have here the slip, okay, times the angular frequency times the magnetizing inductance times the stator current phasor times the rotor current. This is the conjugate. Okay, this is the conjugate. Okay, so what is the approximation? What is the approximation? So by neglecting the copper power losses in the stator and rotor resistance, the relation between the stator and rotor power is immediate. So I will neglect these losses. Therefore, if I compare this power, the stator active power, with respect to the rotor active power, the only difference is the sign. Because of this term, pay attention. This is the subscript rotor and this is the subscript stator. What happened in the rotor active power? This is the subscript stator and this is the rotor. So the only difference is the sign, and the sleep. Okay, so therefore, the rotor active power, taking in neglecting the copper power losses in the stator and rotor, is approximately equal to the sleep times the stator active power, because I have only two different, right? The first one is the sleep and the second one is the sign. Okay, so therefore I will have this approximation. Okay, so I will have this approximation. Okay, so let's simplify this equation. I will say the mechanical power, okay, is equal to the stator active power plus the rotor active power minus, so I will have here the Cooper power losses in the stator. This is the Cooper power losses in the stator minus the Cooper power losses on the rotor. But if I want an approximation, I am neglecting these two terms. I am neglecting, okay? Okay, so the mechanical power is equal to the stator active power plus the rotor active power. Okay, so substituting the rotor into this equation, okay, I will say the mechanical power, okay, is approximately equal to, I will have here the stator active power minus the stator, minus the sleep times the stator active power. So taking out the common factor, the stator, okay, so the mechanical power is equal to 1 minus the sleep times the stator active power. This is an approximation, okay? This is an approximation. Okay, so from the previous class, we demonstrate the 1 minus the sleep, okay, over the sleep is the ratio between the mechanical speed over the rotor speed. Okay, so let's call this equation number 1 and this equation number 2. So isolating this term, okay, the sleep goes to the right side. So I will have here S. So substituting into this equation, I will get the mechanical power. Okay, the sleep goes to the right side. So I will have this is equal to the sleep times the mechanical power over the rotor speed times the stator active power times the stator active power. Okay, so by definition we know this term is 1 over the synchronous speed. Okay, so this is equal to the mechanical speed over the synchronous speed times the stator active power. So this is one way in order to compute the mechanical speed. Okay, the mechanical speed. On the other hand, from the previous class, we know the mechanical power is equal to the electromagnetic torque, okay, times the mechanical speed over the number of poles. Okay, so using this equation, okay, it's possible to derive the following equation. Okay, so for the stator active power is equal to the electromagnetic torque. Yeah, in this case, it's not the mechanical power, is the angular frequency. This is the stator over the number of poles. Okay, and for the rotor, in a similar way, I will say the rotor active power. So I will have the electromagnetic torque. Okay, this is the rotor speed over the number of poles. Okay, over the number of poles. So I will have this approximation in order to compute the mechanical power as a function of the mechanical torque. So that is it. It's better off to use this approximation. Okay, it's better off to use this approximation. Okay, so now I want to analyze the 4-quadrant mode of operation of the double fed induction machine. So from the previous equation, I will have 4 possible combinations. Okay, I will have this one. This one is motor operation. Okay, this one and this one, I will have generator operation. Okay, what is the reason? So let's analyze, for instance, the mode of operation 1. Okay, so if the electromagnetic torque is bigger than 0, the operation is motor. Okay, is motor. If the electromagnetic torque is less than 0, the operation is as a generator. Okay, this is my first conclusion. Okay, yeah. On the other hand, if the slip, in this case is the speed, the slip, sorry. If the slip is less than 0, I will have a hypersynchronism operation. Okay? If the slip is less than 0, it means the mechanical speed is bigger than the stator speed. Okay? In this case, I will have a hypersynchronism operation too. Okay? But what happens if the slip is bigger than 0? I will have a subsynchronism operation. I will have a subsynchronism operation. Okay, this is about the speed. What about the mechanical power, the stator active power, and the rotor active power? So if the mechanical power is bigger than 0, the machine is deliver mechanical power. Okay, in the mechanical power. On the other hand, is less than 0, the machine receive mechanical power. This is for the mechanical power. Okay. What about the stator active power? For the stator active power, if the power is bigger than 0, the machine is receiving power through the stator. Okay, and the rotor, pay attention to the rotor, is the same. If the active power is bigger than 0, the machine is receiving power through the rotor. But pay attention to the mode of operation 2. Okay, pay attention to the mode of operation 2. This is the generator. Okay, so the stator active power is less than 0, and the rotor active power is less than 0. It means the machine is deliver power through the stator. Okay, and for the rotor active power, the machine is deliver power through the rotor. So note that only in the generator mode, a hypersynchronism is possible to deliver power through both the stator and rotor side to the grid. Okay, so I am delivering active power from the stator. I am delivering active power from the rotor. Okay, only for this mode of operation. For the other three modes, the stator is delivering, the rotor is receiving, and so on. Okay, so only in the generator mode, in this case, that hypersynchronism mode of operation is possible to deliver power through both the stator and rotor side to the grid. Okay, this is the main important thing. Okay, so let's analyze the phase diagram for this 4 mode of operation. Okay, let's analyze the phasor diagram. Okay, so I will have, once again, this is the generator mode of operation, this is the generator mode of operation, this is the motor, and this is the motor 2. Okay, so in this case, this figure summarizes the active power flow schematic, okay, as well as the phasor diagram of all the operating modes of the double fed induction machine. Okay, so in this case, the positive stator reactive power consumption, I will assume a stator reactive power consumption for the phasor diagram. Okay, in order to build the phasor diagram, I will assume the stator reactive power is bigger than 0. It means a positive stator reactive power consumption. Okay, so pay attention to this part. Okay, pay attention to this part. Okay, this is the mode 1. The mode 1 is motor operation. Okay, if I have a motor operation, means the input, I will have a stator active power, and the output is the mechanical power. Okay, if I have a motor operation. What about the fluxes? I will have here the stator flux and the rotor flux. Okay, so the stator flux is leading the rotor flux for the motor operation. Okay, what about the generator operation? For the generator operation is opposite. In this case, the rotor flux is leading the stator flux. Okay, so once again, I will have the difference. Okay, if I have a generator mode of operation, the input is the mechanical power and the output is the stator active power. Okay, so pay attention to this part. Let's focus on the rotor and stator fluxes. Okay, so this is motor Okay, this is motor. I will have the second mode of operation. This is generator. Okay, so let's continue here. I will have motor, generator here, and this is motor. So pay attention to the fluxes. Okay, so in this case, the rotor flux is leading the stator flux. The rotor flux is leading the stator flux. And for the first case, this is the mode of operation 1. I will have here the motor operation, okay? So the stator flux in this case is leading the rotor flux in a similar way here, okay? So if this is the generator mode of operation, so once again, the input is the mechanical power and the output is the stator active power. If I have a motor of operation, the input is the stator active power and the output is the mechanical power, okay? And the output is the mechanical power, okay? So once again, this is the mechanical power. The mechanical power, this is the stator active power, and this is the rotor active power, okay? So in order to build the phasor diagram for the fourth mode of operation, okay, I need to plot voltages, current, and flux. So in order to build the phasor diagram, I need to plot voltages, current, and fluxes. Okay, taking into account this, if I have the motor operation or generator operation. Okay. Okay, so let's continue with the per unit transformation. Okay, so in order to define a per unit system, I need to define normally two quantities. Okay. So for this case, for electric machines, I need to define three quantities. The first one is the base voltage. In this case, I will take the line to neutral rated root mean square stator voltage. Okay. I will select the base current. In this case, is the rated stator current. This is in amps. Okay. And finally, I need one quantity more. This is the base angular frequency. Okay, so in this case, I will take the rated stator angular frequency in radians per second. So once I have already defined the three quantities, this is the first one, this is the second, and this is the last one. Okay, with these three quantities, it's possible to derive the rest of the values. Okay, with these three quantities, it's possible to derive the rest of the values. Okay, so let's define the complete per unit system. So let's start with the base flux. Okay, the base flux is equal to the base voltage. Okay, over the base angular frequency. Okay, the base impedance. Okay, so the base impedance is equal to the base voltage over the base current. Okay, the base inductance. The base inductance, okay, is equal to the base flux, okay, over the base current. Okay, the base complex power. The base complex power is equal to 3 times the voltage base times the current base. So as a function of these three quantities, it's possible to derive the rest of the values. Okay, so the base speed, okay, is equal to, this is the base angular frequency over the number of poles. Okay, and the base torque, okay, is equal to the base complex power over, I will have here the, in this case, the base speed. Okay, so I have already defined, this is the per unit system. Okay, if I define the per unit system, so I am able to compute the per unit values. Okay, so I will start from the actual value. So do you remember, by definition, any quantity, the per unit value is equal to the actual value over the base. So I want to convert all quantities to per unit values. Okay, so let's start with the stator side. So we know the stator voltage is equal to the stator resistance times the stator current plus J. I will have here the angular frequency times the stator flux. Okay, but I have in this case, this equation, all quantities are actual values. This is actual value, this is actual value, and this is actual value. So I need to convert to per unit value. So we can transfer the voltage, current, and flux to per unit using the definition. The actual value is equal to the per unit value times the base. That is the way in order to convert to per unit values. In this case, I have only actual values. Okay. Therefore, each quantity I will replace by the per unit value times the base. Okay. So I will say in this case, for instance, I will say the stator voltage, in this case in per unit value, okay, time the base. So I will have here the voltage base is equal to, so I will have here the resistance. So once again, this quantity is split up in the per unit value and the base. So I will have the stator resistance times the stator current. This is the per unit value times the base. Okay, and finally I will have here J. This is the angular frequency times the flux. So once again, the flux, I will have here the flux, the per unit value times the base. Okay, times the base. Okay, so from this equation, isolating the voltage base, okay, I will have the stator. This is the per unit value. This is the stator voltage. Okay, is equal to. So I will have here the stator resistance. This is the current, and the stator current, the per unit value. This is the base. So I will have here the current base. So isolating, I will have current base over voltage base. Okay. So plus, I will have J. This is the angular frequency. I will have this term is the per unit value. This is the stator flux. Okay. Times I will have here the flux base over the voltage base. Okay. So according to our per unit system, okay, so I will have here the following. Okay, so for instance, the flux base is equal to the voltage base over the angular frequency, right? So substituting, this is the flux. So substituting here, this is the flux, right? This is the flux. Okay. So substituting, this is the impedance, right? This is the impedance base. So I will have the impedance base is voltage over the current. I will have current over the voltage. Therefore, I will have the impedance base. So this value divided by this value, this is the impedance base. I will have the resistance in per unit values. Okay, so I will have the stator voltage in per unit is equal to the stator resistance, okay, times this is the per unit value of the core. This is the per unit core. Okay, so plus I will have here J. Okay, so I will replace the flux. Okay, the flux is voltage over speed. Okay, so the flux is voltage over speed. Okay, so I will have here the flux base is equal to the voltage base over the speed base. Okay, so substituting this into this. Okay, what happened here? I will have here the I will simplify the speed, not right? So I will have, for instance, plus J. I will have here the stator flux in per unit value. Okay, the stator flux in per unit value. Okay, so cancel off. This is the speed. with this speed. Okay, so I will get the per unit value. Okay, this is for the stator. In a similar way for the rotor. Okay, so for the rotor, I will have the rotor. I will have here the per unit value. This is the rotor, the per unit value of the voltage. The per unit voltage is equal to the rotor resistance, the rotor current, plus J, and the only difference is the slip, okay, times the rotor flux in per unit value. So in a similar way, it's possible to demonstrate this equation. It's a similar demonstration. Okay, is a similar demonstration. So let's convert to per unit values the fluxes, okay? Let's convert to per unit values the fluxes. So I will have here the stator flux, I will have here the rotor flux. So once again, these are actual values, okay? And the actual value is equal to the per unit value times the base. Okay, so I have actual values. Okay, I will have actual values. Therefore, transforming the fluxes and current to per unit. So I have here the flux, the per unit value. Okay, so let's splitting up the flux. I will have the per unit value. Okay, this is the per unit value times the base. The flux base is equal to the voltage base times the base speed. Okay, so this is the flux base. Okay, this is the flux base. Okay, and this is equal to, so I will have here the stator inductance. Okay, this is the stator inductance, and the current is broken down in the base and the per unit value. Okay, so I will have the base current times the per unit current. This is for the stator. Okay, the same for the inductance. Okay, so I will have here the magnetizing inductance, and this actual value is splitting up in the per unit value and the base. So I will have here the current base. Okay, I will have here the per unit current. Okay, the per unit current. And this is the flux base, right? And this is the flux base. Okay, and this is the flux base. So this expression is equivalent. So isolating this term, isolating to the right side. Okay, isolating to the right side. So I will get the per unit flux, the per unit stator flux is equal to, I will have here the stator inductance. Okay, so I will have here, this is the current base over the voltage base. Okay, times, I will have here to the right side, this is the angular frequency base. Okay, times the per unit value. Okay, this is my first term. What about the second term? So I will have here plus, once again, isolating this term to the right side, I will have the magnetizing inductance. This is the current base. Okay, I will have here the current base over the voltage base times, this is the angular frequency base times the per unit value. Okay, times the per unit value. Okay, so by definition, in our power unit system, I will have here the inductance base is equal to the flux over the current. Okay, the flux over the current. Okay, so substituting here, I will get the per unit stator flux is equal to So this is the actual value. This is the actual value. Yeah, I will have here the base. Okay, therefore I have the per unit value. The stator inductance times the stator current in per unit. Plus, so once again, I will have here the magnetizing. Okay, I will have here the base. This is the inductance base. Therefore, I will have the magnetizing inductance times the rotor, the per unit rotor current. Okay. So in a similar way for the rotor. Okay, so I will have the rotor, the per unit rotor flux is equal to the magnetizing inductance times the per unit value of the stator current plus I will have here the rotor inductance, the per unit value of the rotor current. Okay, so what is missing? What is missing is the electromagnetic torque in per unit. Okay, the electromagnetic torque. So finally, for the electromagnetic torque, so we have already computed the electromagnetic torque. In the previous demonstration, we know is 3 times the number of poles, the imaginary part. Okay, I will have here the rotor flux, this is phasor, times the rotor current. This is the conjugate of the current. This is the actual value. If I want the per unit value, I need to divide by the base torque. Okay, the base torque. Okay, so the base torque from the previous demonstration, from this equation, the base torque is equal to the base complex power over the mechanical speed. Okay, so the base torque is equal to the base complex power over the base mechanical speed. Okay, what about this term? What about the other term? Okay, so let's back. So I will have here the base complex power and the base mechanical speed. So this is 3 times the base voltage times the base current. And the other one is the base angular frequency over the number of poles. Over the number of poles, okay? So I will have here 3 times the base voltage, the base current, over, substituting, I will have here the base angular frequency over the number of poles, okay, over the number of poles. So substituting this into this equation, so I will have the electromagnetic torque, this is the per unit electromagnetic torque, is equal to 3 times the number of poles times the imaginary part, I have the rotor flux, times the rotor current, this is the conjugate, okay, over, so I will have 3 times I have the voltage base, I have the current base, okay, times, so the number of poles goes up over the base angular frequency goes down. Okay, so therefore it's possible to cancel off 3, the number of poles. Okay, and by definition the base flux is equal to the base voltage over the base angular frequency. Okay, so taking this voltage and this one, okay, finally the electromagnetic torque, the per unit value is equal to the imaginary part. Okay, so I will have here This current over the base is the per unit value. This flux over the base is the per unit value. Okay, so I will get the per unit rotor flux times the conjugate of the current, the per unit value. And this is the equation in order to compute the electromagnetic torque. Okay, so in a similar way for the active power, right? In a similar way for the active power. So finally, I will say the per unit value. This is the stator active power. So the stator active power is equal to 3 times the stator voltage times the stator current. Okay, this is the magnitude. Cosine, I will have here the angle. This is the voltage. And this is the angle of the current because I have power, right? If I want to compute the per unit value, I need to divide it by the base. And the base is the complex power. It means 3 times the voltage base times the current base. Okay, times the current base. So this voltage over this voltage, this current over this current is the per unit value and cancel out. Okay, so I will have the per unit stator active power is equal to, so I will have here the per unit value. This is the per unit stator voltage. This is the per unit stator current. Okay, times the cosine. This is the voltage minus the current. Okay, this is for the stator active power. In a similar manner, I will have for the rotor. Okay, so the per unit value is equal to the rotor, the per unit rotor voltage times the per unit rotor current cosine. They will have here the voltage minus the current. Okay, but if we want to compute for the reactive power, for instance, for the stator and for the rotor, okay, I will change cosine by sine, and this is the way in order to compute the active and reactive power. So I have already computed the whole per unit values in the doubly fed induction machine. Okay, so in order to make clear this equation, let's work in our first problem. Okay, let's work in our first problem. Okay, so Mrs. Sola, could you please read over the example 1?
Yes, doctor. This example illustrates the steady state of a 2 megawatt doubly fed induction machine. The operating point is chosen as the rated stator power generating with 0 stator reactive power, 50 Hz of grid frequency, and sleep equal 0.25 sleep. Hypersynchronous speed. Data of the doubly fed induction generator is shown in the following table.
Okay, please continue.
Letter A, plot the phasor diagram of a doubly fed induction machine. Letter B, compute rotor active and reactive powers as well as the torque. Letter C, find rotor real voltage and current. Letter D, finally compute the minimum DC bus voltage to handle the rotor voltage amplitude.
Okay, thank you. Okay, so let's start the solution of this problem. So I will have here a doubly fed induction machine. This is the rated power is 2 megawatts. So for this problem, I will have two tables. In this case, I will have the synchronous speed is 50 Hertz. Okay, so the problem is asking me For this character, this is the rated characteristic from the manufacturer. Okay, I will have, this is the data of the machine. Okay, this is the data. For instance, this is the constant, is something like a turn ratio. This is the stator resistance, the stator leakage inductance, the magnetizing inductance. This is the data for this machine. Okay, so the machine is operating. The machine is operating to this power. But pay attention, is hypersynchronous speed. Okay, hypersynchronous speed. So in this case, the operating point is chosen as the rated stator power generating. Okay, so therefore I will have here the stator. The stator active power is equal to negative 2 megawatts, because I am operating at hypersynchronous speed. Okay, according to the problem, the stator reactive power is equal to 0, because it's generating with 0 stator reactive power. Okay, the frequency of operation is equal to 50 hertz. Okay, the sleep is hypersynchronous, means negative 0.25. The number of poles, according to the problem, is equal to poles. Okay, this is the data from the table. And besides, the rated stator voltage is 690 volts, and the rated stator current is 1760 amps. Okay, so this is the line-to-line nominal stator voltage, and this is each phase nominal stator current. This is the nominal stator current. Okay, so what else? I need the stator resistance. Okay, the stator and rotor inductance. Okay, so I need the stator and rotor inductance. Okay, and besides, the magnetizing inductance and the rotor resistance. So we have here the rotor resistance and the stator resistance. Okay, so according to this problem, the rated stator voltage is this value and this current. So let's say I will have something like a methodology. Okay, in order to plot the phasor diagram, I will have something like a methodology. Okay, what is the methodology? Yeah, first of all, the stator voltage and current. So I need to compute the stator voltage and current. Normally, this is data. Okay, this is my first step. Okay, my second step is to compute. Let's call, it's not the step, this part is not the step, because normally this is data. Okay, so let's call 0 step. Okay, but I will continue. This is my first step. I will compute the stator flux. Okay, and then I will compute the rotor current. Okay, my next step is to compute the rotor flux, and finally the rotor volts. That is the way in order to plot the phasor diagram. Okay, that is the way in order to plot the phasor diagram. Okay, so let's start with the first question. My first question is to plot the phasor diagram of the double fed induction generator. Okay, so therefore, firstly, the machine is supposed to be delivering 2 megawatts to the grid. Okay, so we have already said the stator active power is equal to negative 2 megawatts. So with the rated stator voltage, I need the line to neutral voltage, because from the data I have the line to line voltage, right? I want to carry out the analysis per phase. Okay, so from the problem I have the line to line voltage. What I need is the line to neutral voltage. Okay, so therefore, with the rated stator voltage, I will have this is phasor. By the way, I will have this is the reference to. Okay, so I will have here over the square root of 3 because I need the line to neutral voltage. Okay, so this is equal to 398.4 with 0 degrees because it's the reference. Okay, so do you remember in order to plot the phasor diagram, the stator voltage always for the fourth mode of operation is the reference. Okay, is the reference. Okay, so according to the methodology, normally this is data and this is data. Okay, so I have now the stator volts. So this is indicate that when the reactive power is 0, okay, the stator current phasor yields. So pay attention to this part. Pay attention to this part. So I will have here the stator. Okay, if the stator reactive power is equal to 0, it means I will have here the stator phasor. This is the stator voltage, this phasor, and the current is opposite because the stator reactive power is equal to 0. This indicates that when the stator reactive power is equal to 0, is choosing the stator current phasor yields this phasor diagram. Okay, so therefore the stator active power, okay, so is equal to 3 times. I will have the real part. This is for the active power. I will take the real part of the stator voltage times the conjugate of the stator current. Okay, so taking the real part, I will get the stator active power. Okay, so this is equal to 3 times. I will take the real part. Okay, so the stator active power according to the problem is 2 megawatts, right? So I will have here 2 megawatts. Yeah, the stator voltage, we have already computed this value, is this value. Okay, so I will have 398.4 with 0 degrees times the conjugate of the current. Okay, so isolating from this equation, the stator current is equal to 1673.8 180 degrees amps, because this is a hypersynchronous operation. Okay, because this is a hypersynchronous operation. Okay, so let's work in per unit values. Okay, let's work in per unit values. So the base values, I will assume the base values, so the base voltage, for instance, okay, is equal to the stator voltage. So this is the 398 less back 0.4. This is the base voltage. Okay, what is the base current? Is the magnitude. Okay, so once again, let's back. I have, let's take the ray values, right? Let's take the ray values. So I will have, this is the current and this is the voltage, but I need the line to neutral voltage, right? So I will take the base current. Yeah, the base current is equal to the stator current, and this is equal to 1760 amps. Okay, with these two quantities, I am able to compute the base complex power. By definition, is equal to 3 times, and this is the base voltage, okay, times the base current. Okay, so 3 times the base voltage times the base current is equal to 2.1. I will have MVA. This is the base complex power. Okay, substituting these two values into this equation. Okay, what about the base frequency? Okay, according to the problem, the frequency of operation is 50 Hertz, right? So I will have 50 Hertz. Okay, so let's compute the other bases. Okay, for instance, the base flux. Okay, so the base flux by definition is equal to the base voltage, okay, over the base speed. Okay, so therefore, I will have the base voltage and the speed is equal to 2 times pi times the base frequency. Okay, so we know this value is 398.4 volts over 2 times pi times the frequency, 50. Okay, therefore the base flux is equal to 1.26 Webers. Okay, this is the base flux. Okay, let's continue with the other quantities. For instance, the base torque. Okay, so let's continue with the other quantities. Okay, so I will have here the base torque. Okay, the base torque by definition is the base complex power over the base speed over the number of poles. Okay, so I will have 2.1, this is MVA, over 2 times pi times 50 is 314.16. 2 times pi times 50, the frequency of operation is 50 over the number of poles over 2. Okay, so the base torque is equal to 13.3 Newton meter. Okay, this is the base torque. So in order to build the phasor diagram, let's start computing the stator flux. Okay, so consequently, the stator flux can be calculated directly from this equation. Okay, so do you remember from the methodology? From the methodology, my first step is to compute the stator flux. Okay, so from this equation, we have already derived this equation, the stator voltage minus the stator resistance times the stator current is equal to J times the speed. This is normally the angular frequency. In order to make a difference, I call the speed, but the right meaning is the angular frequency, okay? Because this is the speed, okay? Anyway, I will say the speed, okay? So times the stator flux. Okay, so from this equation, isolating the stator flux, this is the methodology, okay? The first step is to compute the stator flux. Okay, so what about the voltage? This value is 398.4 with 0 degrees minus. I will have, this is the stator resistance, so let's back to the table. This is the stator resistance, milliohms. In this case, is 0.0026. Okay. So I will have 0.0026 times. What is the stator current? The stator current is, we have already computed. I have already cleared, is 1673.8. I will have 180 degrees. 180 degrees over isolating. I will have here J, and the speed is 2 times pi times the frequency of operation. In this case, 314.16. Okay, So the stator flux computing is equal to 1.28, sorry, negative 90 degrees. Okay, this is the actual value. Okay, what is the base of the flux? What is the base? I have already cleared this, but the base is 1.26. If I want the per unit value, I need to divide it by the base. Therefore, in per unit value, I will have 1.01 with negative 90 degrees. So my first step is to compute the stator flux. Okay, my first step is to compute the stator flux. What is my second step? What is my second step? According to our methodology, my second step is to compute the rotor current. Okay, I need to compute the rotor current. So let's continue. Let's continue here. Let's compute the rotor current. Okay, so for the rotor current, we have already derived the equation. Okay, so I will have the rotor current. Okay, the rotor current is equal to the stator flux minus the stator inductance times the stator current over the magnetizing inductance. Okay, so according to the program, this is data from the manufacturer. So I will have here the stator, this is the magnetizing inductance, and this is the stator inductance. Okay, and this is the stator inductance. Okay, so substituting the values, I will have 1.28. I will have a negative 90 degrees minus I will have 0.002587, okay, times this is the stator current 1673.8 with 180 degrees over the magnetizing inductance 0.0025. Therefore, the rotor current is equal to 1807.4 with negative 16.5 degrees. This is amps. Okay, so in order to compute the per unit value, I need to divide it by the base. Okay, so by definition, the actual value and the base is the rated value. Okay, so therefore, the per unit rotor current is equal to 1.02, okay, with negative 16.5 degrees. Okay, this is the per unit value. Okay, following the methodology, once I compute the rotor current, I will continue with the rotor flux. Okay, I will continue with the rotor flux. Okay, so we have already derived the rotor flux equation is equal to the magnetizing inductance, okay, times the stator current plus the rotor inductance times the rotor current. Okay, so the rotor flux is equal to the magnetizing is 0.0025 times the stator current 1673.8 with 180 degrees, okay, plus the rotor inductance is 0.002587 times the rotor current. So I will have 1807.4 with, I will have 16.5 degrees. Okay, so finally the actual value is 1.358 with negative 77.4. This is the flux. Okay, so in order to compute the per unit value, by definition is the actual value over the base, and our base is 1.26. Okay, so the per unit rotor flux in per unit values is 1.07 negative 77.4 degrees. Okay, so according to our methodology, let's back. So we have already computed the voltage, the current, the stator flux, the rotor flux. So finally, the rotor voltage. Okay, so finally all the phasor are computing with the rotor voltage. Okay, so the last phasor is the rotor voltage. Okay, so we have already derived the equation. So we have here the rotor resistance times the rotor current. This is phasor plus J. I will have here the slip. This is the angular frequency and the rotor flux. That is the way in order to compute the rotor voltage. Okay, so substituting the values. So I will have 0.0029 okay times the rotor current is 1807.4 with negative 16.5 degrees plus J. Okay, the slip is negative because it's so hypersynchronous operation. So I will have 0.25. This is the slip. The speed is 314.16. Okay, times the rotor flux. So I will have 1.358 with negative 77.4 degrees. Therefore, the rotor voltage is equal to 102.2 with negative 165.9 degrees. This is volts. If I want to compute the per unit value, is equal to the actual value over the base, and the base is 398.4. This is the line to neutral voltage, right? Okay, so this is equal to 0.25 with negative 165.9 degrees. So we have all phasor, okay? We have all phasor. So let's depict it in the figure. The phasor diagram is depicted in the following figure, okay? Okay, so I will have, this is the stator voltage. Okay, this is the stator voltage. I will have the stator current. Okay. Later on, my first phasor is the stator flux. Okay, so I will have the stator flux. And for the stator flux, I will have 90 degrees. Okay, so later on we compute the rotor current, okay? And the rotor current is this one. This is the rotor current. Okay, and the angle for the rotor current is 16.5 degrees. Okay, so and then we compute the rotor flux. And the rotor flux is here. Okay, and the rotor flux, I will have this angle is 77.4 degrees. This is the rotor flux. And then I will have here, and then I will have here finally the rotor voltage. Okay, so for the rotor voltage, I will have, this is the phasor. Okay, this is the rotor voltage, and the angle is 165.9 degrees. Okay, this is my first question. This is my first question. My first question is to plot the phasor diagram of the doubly fed induction generator. Okay. So do you have any question, guys? Is that clear, Mr. Salazar?
Yes, that's clear.
Okay, thank you. So let's continue with the second question. The second question is to compute the rotor active and reactive power as well as the electromagnetic torque. This is my second question. Okay. So let's start computing the rotor active power. So from the computing phasor, the rotor active and reactive power as well the torque can be found in the following way. So I will say the rotor active power, okay, is equal to 3 times taking the real part. Okay, I will have the rotor voltage, okay, times the conjugate of the rotor current. Okay, so that is the way in order to compute the rotor active power. Okay, so we have already computed these two phasors, right? So I will say the rotor active power is equal to 3 times taking the real part. Okay, I have here the rotor voltage is equal to 102.2 negative 165.9 degrees. Okay, times I will have 1,874, 1,807.4. I will have 16.5 degrees. Okay, so this is the conjugate, right? This is the conjugate. So I will have here the conjugate. Okay, so therefore the rotor active power is equal to negative 0.55, okay, megawatts. Okay, this is the rotor active power. If I want to compute the per unit value, so once again the definition, the actual value over the base. So the per unit value is equal to the actual value and the base is 2.1 MVA. Therefore, the per unit rotor active power is equal to negative 0.26. This is the per unit value. This is the active power. What about the reactive power? So in order to compute the reactive power, I will take the imaginary part. Okay. I have here the rotor voltage times the conjugate of the rotor current. So in this case, I will take the imaginary part. Okay, I will take the imaginary part. Okay, therefore, the reactive power, I will have the same values, right? I will have the same values, but in this case, I am taking the imaginary part. Okay, so the rotor reactive power is equal to 23.4 kilobar. Okay, this is the rotor reactive power. If I want to compute the per unit value, so this is the actual value divided by the base, over the base. Okay, therefore the per unit value is equal to 0.011. Okay, so pay attention to this value. It means that the machine is being magnetizing through the rotor. Because I have this small value means that the machine is being magnetizing through the rotor, okay? Through the rotor. Okay. Okay, so finally, let's compute the electromagnetic torque. So the electromagnetic torque, so I have many expressions, right? I will use this expression, 3 times the number of poles times the magnetizing inductance over the stator inductance times the imaginary part. So I will have here the stator flux, okay, times the conjugate of the rotor current, phasor, okay, phasor. Okay, so the electromagnetic torque is equal to 3 times the number of poles is equal to, okay, the magnetizing inductance, we have already used this value, is 0.0025 over the stator inductance is 0.002587 times the imaginary part. So the flux, we have already computed the flux, is 1.28 negative 90 degrees times, I will have here the conjugate of the rotor current, okay, so 1807.4 with negative 16.5 degrees. This is the conjugate, okay, this is the conjugate. Okay, therefore, the electromagnetic torque is equal to negative 12.9, I will have K Newton meter. K Newton meter. Okay, so in order to compute the per unit value, by definition is equal to the actual value over the base, and the base is equal to 13.3 K Newton meter. Okay, so this is equal to negative 0.97. Okay, 0.97. Okay, so let's analyze the following. Okay, what is the grid active power? Okay, so the total power generated by the Doubly fed machine is the grid active power, and this is equal to the rotor active power plus the stator active power, and this is equal to negative 0.55 minus 2, and this is equal to negative 2.55 megawatts. Okay, so let's continue with the next question. The next question is find the rotor real voltage and current. Okay, it means I need to use, if I want to compute the real values, I need to refer to the rotor side. For that, I will use the turn ratio. So do you remember in the previous class, U is something like the turn ratio, right? Okay, it's something like the turn ratio. Okay, so let's continue with the question 3. Okay, so in this case, the rotor magnitudes are referred to the stator. So if I want to compute the real current and voltage, I will use the factor mu. So in this case, this factor must be taken into account as follows. So I will say the mu factor is equal to, according to the problem, is this value, 0.34. Okay, so I will have 0.34. Okay, so I need to refer to the stator, right? The rotor magnitude, the rotor magnitudes are referred to the stator, so I need to refer to the rotor, okay? So I will have here this is the rotor voltage. I need to refer, in order to compute the actual values, I will use the turn ratio, right? This factor. And for the current, the same. I will have the factor times the rotor current. Okay, times the rotor current. Okay, so we have already computed this value is 102.2 and the angle is negative 165.9 degrees and the factor is 0.34. Therefore, the voltage is equal to 300.6 165.9 volts. So what is the frequency of operation of the rotor? What is the frequency of operation of the rotor? Okay. I will have here, let's compute the current. So I will have 0.34 times the rotor current. So we have already computed this value, 1807.4. I will have with negative 16.5 degrees. Okay. So this is equal to, I will have 614.5 negative 16.5 amps. Okay, so once again, my question, what is the frequency of operation of the rotor? So pay attention, I am referring from the stator to the rotor side. Okay, so do you remember, in order to derive the equivalent circuit, we need to work with the same frequency. So in the first step, we compute the equation of the stator at the stator frequency. Later on, we compute the rotor equation at the rotor frequency. Yeah, in order to work at the same frequency, we need to use the slip. Okay, so finally, we get the equivalent circuit at the stator frequency. Okay, what is the stator frequency, by the way? 50 Hertz. But now, in order to have the real values, the actual values, I need to refer once again from the stator to the rotor using the turn ratio. In this case, I call the factor mu, but it's something like the turn ratio. But now the values are referred to the rotor side. Therefore, what is the frequency of operation? Is that clear? The question, Mr. Rocha, how to compute the frequency of operation?
Okay, doctor. Is the same 50 hertz?
Yeah, so pay attention to this part. Pay attention to this part. If I have this value, and this value, the frequency of operation is 50 Hertz. Okay, but because I am using the turn ratio, it means I am referring from the stator to the rotor side. So now these values are referred to the rotor side. So in this case, I know I have different frequencies, right? Because I have the real values. This is on the rotor side. Okay, so what is the frequency of operation? By definition, the rotor frequency is equal to the slip times the stator frequency. Okay, it means 0.25 times 50. So the rotor frequency is 12.5 Hertz. So in the beginning, if I have these values, the frequency of operation is 50 Hertz. Because now I am referring to the rotor side, now the frequency of operation is 12.5 Hertz. Is that clear, Mr. Rocha?
Yes, doctor.
Okay, so any question, guys? Is that clear? So finally, the last question. The last question is compute the minimum DC bus voltage to handle the rotor voltage amplitude. Okay, this is my final question. Okay, yeah, so from the required DC bus voltage perspective, taking into account that these phasors are, in this case, root mean square values, ideally, Okay, the required minimum DC bus voltage to handle this rotor voltage amplitude would be, so I will have here, this is the root mean square value of the voltage is equal, by definition, is equal to the peak value over the square root of 2. Okay, so therefore, if I want to compute the bus voltage is equal to the square root of 3 times the rotor voltage times the square root of 2. Okay, so therefore, the bus voltage is equal to the square root of 3. The rotor voltage is 300.6 times the square root of 2, and this is equal to 736 volts. Okay, so this example shows that with the machine design to generate, in this case, 2 megawatts and 0.55 megawatts of power through the stator. This power comes from the stator, and this power comes from the rotor, right? The rotor side converter must be able to handle this value. Okay? This value. In this case, the machine is magnetizing through the rotor. Okay, so once again, let's back to the question. Compute the minimum DC bus voltage to handle the rotor voltage amplitude. So now I am talking about the converter. What is the voltage on the converter, right? Okay, so this is the definition of the root mean square value. Okay, so what is the perspective from the required DC bus voltage? I need to take into account the phasor are root mean square values. So what is the minimum DC bus voltage to handle this rotor voltage amplitude? Is this value. Okay. Therefore, I will need this value, and this is the voltage at the bus. Okay, this is the voltage at the bus. Guys, do you have any question? Any question, guys? Okay, so if you don't have questions, so Mr. Mejia, could you please read over the problem, the example 2? Okay, so let's continue with the example 2. Mr. Mejia, please read over.
Okay. Example number 2, parameters of 2 megawatts for DFEM, double feed induction machine. Table show the characteristics and parameters of a 2 megawatt double feed induction machine. All these characteristics and parameter values are subject to how the manufacturer has designed the machine. However, it is typical to find some basic common feature among the brands. The rate active power of the machine is often associated with the rated generator stator active power. Note that the machine can be generating or motoring more active power than the rated power, depending on the speed or sleep. Stator power plus rotor power. In a sense, the rated power can be understood as the rated power of the machine at the synchronous speed, that is, with rotor power equal 0 at sleep equal 0. Compute total rated power, power factor, and rated rotor power exchange.
Okay, and this is the data, and this is the same data for the problem 2. And this is the same data from the problem 2. Okay, so pay attention. Once again, this is the rated power, 2 megawatts. Okay, I will have the rate stator voltage. So I need to compute the mechanical power. So do you remember we have an approximation, right? So we have an approximation. So the mechanical power, okay, is equal to the stator active power plus the rotor active power. And the approximation is equal to the stator 1 minus the slip. Okay, so according to this problem, I will have the slip what is the stator active power? Is 2 megawatts. Okay, so in this case, the rated active power is associated with the total rate power. Okay, so this is the stator plus the rotor. Okay, so this point is located at the maximum allowed slip at the hypersynchronous. Okay, if I am operating a hypersynchronism, typically this value is plus negative 0.3. This value is 0.3. Okay, because in this point of operation, or this point of operation is located at the maximum allowed slip at the hypersynchronous. Okay, so normally this value is 0.3. So therefore, in order to compute the mechanical power is equal to 2 megawatts, 1. In this case, I will take negative because I am operating in hypersynchronous mode of operation. So I will have plus 0.3. Okay, and therefore the mechanical power is 2.6 megawatts. Okay, 2.6 megawatts. Okay, so the second question is to compute the power factor. Okay, the second question is to compute the power factor. Okay, so by definition, the stator active power is equal to the square root of 3 times the rated voltage times the rated current times the power factor. Okay, so from this equation, isolating the power factor is equal to, I will have here the stator active power over the square root of 3 times the rotor voltage times the rotor current. Okay, the stator active power is 2 megawatts. Okay, over the square root of 3. What is the value of the rotor voltage? So I go back to the problem. Yeah, I will have this is the voltage and this is the current. Okay, so I will have this is the line-to-line voltage, okay, times the current. Therefore, the power factor is equal to 0.95. Okay, but the most important thing is because of this point of operation, okay, in other words, this point of operation is located at the maximum allowed slip at the hypersynchronous. Okay, so typically this value is 0.3 for this point of operation. Okay, but in order to compute the power factor, I will always use the definition, right? I will always use the definition. Okay, besides, because this typical slip range operation is, in this case, positive negatives 0.3, implies that the rated rotor power exchange is, in this case, 30%. Okay, of the rated stator power, of course. So in this case, this leads to the rated rotor current smaller than the rate stator current. Okay, so due to this slip, okay, I will have this is the rate of the rotor power exchange. Okay, due to this slip, This is the rated rotor power exchange in addition, okay?